Hi everyone, welcome back to Quantum, where we explore the fascinating world of quantum mechanics and computation. Today, we'll summarize 6 essential topics in quantum mechanics and quantum computation. We'll cover concepts like Hilbert spaces, quantum postulates, the discovery of spin, entanglement, and the groundbreaking principles of universal quantum computation. Let's get started. Chapter 1: Hilbert space and linear operators. We begin with the Hilbert space, the mathematical foundation of quantum mechanics. This is where quantum states live and evolve. A Hilbert space is a complex vector space with an inner product, allowing us to measure things like probabilities and overlaps between states. Key features of Hilbert spaces: vectors in Dirac notation. Quantum states, or qets, are represented by symbols like ket v. These vectors represent possible quantum states. Inner product. This is the overlap between two states, written as the inner product of v and w. It defines orthogonality, where the overlap is 0, and normalization, where the state has a total probability of 1. Basis and completeness. Basis vectors span the space, meaning every quantum state can be written as a combination of these basis vectors. Next, we have linear operators, which act on these vectors to compute physical properties. Hermitian operators are used for observables, such as energy, and always give real results. Unitary operators describe time evolution while preserving the total probability. For example, when a linear operator A acts on a vector, it transforms it into another vector while preserving its structure. This operation can often be written as matrix multiplication. Chapter 2: Quantum postulates, von Neumann processes, and the Heisenberg picture. Quantum mechanics rests on 5 postulates, which describe quantum states, measurements, and dynamics. 2 processes govern quantum behavior. Process 2, unitary evolution, the smooth, deterministic evolution governed by the Schrödinger equation. Process 1, state collapse, the probabilistic collapse during measurement. In the Heisenberg picture, operators evolve over time while states remain fixed. Its foundation lies in the Heisenberg algebra, where the commutator of position and momentum is given as the commutator of x and p equals I times h bar. This algebra encodes the structure of quantum mechanics and allows us to transition from classical to quantum mechanics through canonical quantization. Conversely, as h bar approaches 0, quantum mechanics transitions back to classical physics in the semi-classical limit. Chapter 3: The discovery and quantum mechanics of spin. Spin, an intrinsic quantum property, was discovered in the Stern-Gerlach experiment. By passing silver atoms through a magnetic field, the beam split into 2 paths, revealing that electrons have an intrinsic angular momentum called spin. Key points about spin: quantized nature. Spin half particles like electrons have 2 states, spin up and spin down. Mathematical framework. Spin is described using the Pauli matrices, which are essential for spin algebra. Representation theory. Spin states form irreducible representations of the rotation group SO3 and its quantum extension, SU2. This representation theory explains why spin can take half-integer values, unlike orbital angular momentum. The Stern-Gerlach experiment demonstrated how quantum states collapse into discrete outcomes upon measurement, highlighting the probabilistic nature of quantum mechanics. Chapter 4: EPR experiment, quantum entanglement, and Bell's theorem. The EPR experiment introduced the concept of entanglement, where 2 particles remain correlated even when separated by large distances. If one particle's state is measured, the state of the other is instantly determined, a phenomenon Einstein called spooky action at a distance. At the heart of this debate are 2 fundamental hypotheses: reality or classical reality. Physical properties, such as the spin of a particle, exist independently of observation. This assumption implies that these properties are intrinsic to the particle and are not created or influenced by the act of measurement. Implicit in this hypothesis is classical logic, where measurement outcomes are deterministic and adhere to fixed probabilistic rules. Locality or local causality. No influence or signal can travel faster than the speed of light. In other words, the measurement of one particle cannot instantaneously affect the state of another distant particle. This hypothesis implicitly relies on free choice, meaning the choice of measurement settings for one particle is independent of any prior or simultaneous events at another location. Together, These assumptions form the framework of local realism, which seeks to explain quantum phenomena using deterministic and local principles. Bell's theorem challenges these ideas by showing that quantum mechanics violates the predictions of local realism. Bell derived an inequality that must be satisfied if local realism holds. However, quantum mechanics predicts correlations that exceed these bounds. For example, entangled particles exhibit correlations in their measurement outcomes that cannot be explained by any local hidden variable theory. Experiments, such as those by Aspect in the 1980s, confirm these violations of Bell's inequality, demonstrating the fundamentally non-local and probabilistic nature of quantum mechanics. This forces us to abandon either reality or locality, or both, as classical assumptions fail to describe the quantum world. Chapter 5: Qubits, Block Sphere, and Quantum Gates. A qubit is a quantum version of a classical bit, existing in a superposition of 0 and 1. Its state is represented as a linear combination of the states 0 and 1, weighted by probabilities. The block sphere is more than a visualization. It is the precise state space of a qubit. Every point on the sphere corresponds to a pure quantum state. Transformations on the block sphere, like rotations, correspond to quantum gates. Key gates include Hadamard gate creates an equal superposition of 0 and 1. C0 gate entangles two qubits, flipping the target qubit based on the control qubit's state. Superposition and entanglement form the backbone of quantum algorithms, enabling computational advantages over classical systems. Chapter 6: Universal Quantum Computation. Universal quantum computation relies on three fundamental principles. 1. Two-level decomposition. Any unitary operation on a multi-qubit system can be decomposed into a sequence of two-level unitary matrices, each affecting only two quantum states at a time. This decomposition simplifies complex operations, breaking them into smaller, fundamental steps that are easier to implement within quantum circuits. 2. Universality of single qubit and CNOT gates. Any two-level unitary matrix, which acts on a two-dimensional subspace of the Hilbert space, can be implemented using a combination of single qubit gates and CNOT gates. Together, these gates form a universal set capable of constructing any quantum operation on multiple qubits. Single qubit gates handle the manipulation of individual qubits, while CNOT gates enable entanglement, a key resource in quantum computation. 3. Approximating single qubit unitary matrices. Using the Hadamard H and T gates, any single qubit unitary operation can be approximated. These gates allow precise rotations and transformations on the block sphere, enabling full control over individual qubits. The Solovay-Kitaev theorem ensures that this approximation is efficient, requiring a number of gates that scales logarithmically with the desired accuracy. This efficiency makes H and T gates foundational for building practical quantum circuits. These topics unveil the profound nature of the quantum world. They form the foundation for understanding quantum mechanics and utilizing it for computation. If you enjoyed this summary, please like, share, and subscribe to Quantum. Let me know in the comments what topics you'd like to explore next. Thanks for watching, and see you in the quantum realm.